Have you ever tried catching a cricket ball and then catching a shot put ball, both coming at you with the same speed? Your hands can easily stop the cricket ball, but the shot put? That could hurt. But why is that? This real-life difference is explained by the concept of momentum, a measure of how much motion a body carries. And not all motion is equal. The mass and the speed together decide how hard it is to stop something. So if you've ever felt pushed back while stopping a rolling tire or while catching a fast-moving ball, you've experienced momentum in action. Now let's build on that intuition. In physics, the linear momentum of a body is defined as the product of its mass and velocity. It is denoted by the symbol p. The mathematical form is P equals m into v, where P is momentum, m is mass in kilograms, and v is velocity in meters per second. Since velocity has direction, momentum is also a vector quantity. It doesn't just have a size, it also points in a direction. So a bullet and a car might have the same speed, but the car's massive weight gives it far more momentum, which is why stopping it takes more force and time. Let's go deeper. Why is momentum so important? Well, it tells us how difficult it is to stop a moving body in a given time. And this is tied directly to Newton's second law, which says force equals rate of change of momentum. Or simply, F equals delta P by delta T. So, greater the momentum, greater the force required to stop the object quickly. That's why high-speed collisions are dangerous, because the force of impact depends on how much momentum is being lost. From car crashes to rocket thrusts, momentum is what connects mass, speed, and force in one elegant relationship. Now let's talk about how we measure momentum. From the formula P equals m into v, we get unit of momentum equals to kilogram meter per second. Dimensional formula is mLt to the power minus 1. So if you're solving a problem where a body of mass 10 kilograms is moving at 5 meters per second, its momentum is P equals 10 into 5 equals to 50 kilogram meter per second. This makes momentum a very usable tool in calculations, not just a concept, but a quantitative bridge between motion and force. Here's something fascinating. Two cars with the same speed but moving in opposite directions do not cancel each other out. Why? Because momentum is a vector, it includes direction. So if two bodies move toward each other, one with momentum plus 20 and the other with minus 20, their net momentum is 0, but the collision still happens because of opposite directions. This is why direction matters, especially in collisions, explosions, and motion in systems like rockets or machinery. As you can see in the diagram, momentum vectors point in specific directions, helping us visualize interactions between bodies more accurately. Let's bring this to life with a quick problem. Problem: a truck has a mass of 1000 kilograms and moves at a speed of 25 meters per second. What is its momentum? Solution: using the formula P equals m into v, we get P equals 1000 into 25 equals to 25,000 kilogram meter per second. So the truck is carrying 25,000 units of momentum, which explains why it takes a long distance to stop, even with brakes applied. This kind of calculation is crucial in road safety design, sports science, and even engineering design for motion systems. Before we wrap up, think about this: why do martial artists break bricks with fast punches, not heavy ones? Momentum. Why do cricketers use follow-throughs after hitting the ball? To control momentum. Why do astronauts float in space but push off with tiny movements? Because of momentum conservation. From space launches to airbag systems to catching a fast ball, momentum is everywhere. It's not just a physics term, it's how nature handles moving mass. And understanding it gives us the power to calculate, predict, and even control motion.